All right, hi everybody. It's Ilya from NEAR, and we're here with Stan from SKALE to talk about how SKALE scales with Ethereum. Stan, do you want to introduce yourself and then we can dive in?
Okay, yeah. So let me just a couple of minutes tell you guys about myself, because then you'll better understand, what I'm interested in and what kind of things SKALE does. So I'm the CTO of SKALE, but like my history started like when I was still in the high school. I did lots of mathematics, physics, as probably many children in the former Soviet Union, like I'm a typical, I would say, like a nerd in the sense that I did lots of science. So I did math, physics when I was in high school. I participated in different competitions in math and physics. Then I studied at the physics department in Ukraine. I did PhD in physics, again, like in theoretical physics in Germany. Then I was working at Los Alamos National Lab in New Mexico, in the States. And then at Stanford University, all was about physics. So mathematics, physics. And then at some point, I was at Stanford, and at that time, it was like close to the first bubble. Everyone was doing like startups and making lots of money and excited. And I moved from academia to more like startup life. Pretty much for my entire life, I was doing startups, different types of startups. So I worked at a startup which was started by Professor Dan Bonnet at Stanford. It was called Ingram Networks, and then they raised about $50 million total. That was a network encryption device. So at that time, people needed to encrypt stuff, and we started as encrypting websites, but then we pivoted to database encryption and created this hardware box, which was used at banks to encrypt databases. And at some point, the startup got acquired by a company called SafeNet, and now it's still a pretty well-selling device. So by SafeNet, they're selling it to banks. So if you go to a bank as a database and there's some information in the database, there's a very significant chance that it's encrypted using its hardware box. So after that, I actually started my security lab. And this lab was doing research together with the US government and also certification with the US government. So we certified different types of crypto, starting from software, crypto software to hardware. So we worked on things like Mozilla browser, crypto library, another crypto library which is called OpenSSL. We worked on crypto chips from different companies such as Cavion Networks, Marvel, all kinds of crypto. And in all of those cases, we tried to understand whether a particular mathematical algorithm conforms to government standards, whether there are any types of vulnerabilities. So it was very interesting kind of work. And then I was working in this crypto lab for a while. And then after living for many years in Silicon Valley, I got seed funding for a startup which was doing Wi-Fi security. And I kind of got back to Ukraine and hired people there. And it was a software product, which secured large Wi-Fi installations. So our product got installed in many places such as London Underground and Thames River in London, in New York City and Manhattan in the former telephone booths, in San Francisco, city of San Francisco, city of San Jose, in shopping malls. So it was a pretty good product. And we ended up selling this product to a telecom company in the UK, in London. And after that, I was looking to do something else. So I went to VCs, and at that time I knew some VCs. So I knew Mike from Floodgate, Mike Maples, and I knew Rick Thompson from Signia Ventures. So we were thinking what to do, and we started doing big data. So we did a big data platform and build a product, but we were competing against similar platforms by Google, and also AWS had a similar big data platform.
Yeah,
and it was very hard for us because a small startup, you're like, wow, here's my big data platform, but it's Google and it's Amazon. So it was not doing well, although the technology was doing well, but competing against very large companies was not easy. And so we are kind of thinking about like putting down the startup or doing something about that. But at that moment, all of the crypto revolution, it was I think in 2017. So all of the crypto stuff suddenly started happening, and we went back to our investors, to Mike Maples from Floodgate and to Rick Thompson from Signia, and they said, yeah, you guys have to, you know this big data stuff and crypto, and like you have to go into this crypto space. And then we kind of started to learn and understand what problems existed in this crypto space and how we can find the product market fit, how we can actually find something that people needed. So we started researching Ethereum and the scalability problems and this and that. And then we realized, I think as many people, that definitely the scalability is a problem. So transactions are expensive on Ether. Also takes time to finalize. So typical Ethereum transaction, if you want to make sure it's actually okay, you wait maybe a minute or 2 minutes. If you don't want someone else to come and kind of
reorder the chain.
Yeah. So we kind of were thinking about it, and we kind of said, okay, here's the scalability problem, and we talked to our investors, and investors started, okay, said, yeah, do this, and then we started to kind of first we understood the problem, and then started to understand the product market fit. What should we do? And so we made several decisions, and one of the decisions we made was to focus on ETH ecosystem. So instead of creating our own blockchain, we decided to create this product, this complementary network, which is kind of works with ETH, 100% compatible, because we saw like all this momentum, like hackers and people and like coding and using these languages like Solidity and EVM, and like we saw like lots of excitement. So we had this theory that it's like JavaScript, like if you guys remember, like when the first browser was released, there was JavaScript, which probably wasn't the perfect language, but there was so much momentum in hacker community for programmers and stuff that people kind of kept on modifying JavaScript. And although like companies like Google, for instance, like Google tried to come up with a different language. There was this language, for instance, Dart from Google, which
so it's way later.
Yeah, but later, but they couldn't actually get momentum. So what ended up with JavaScript is now TypeScript from Microsoft. So JavaScript kind of took this more like evolutionary approach, and Dart kind of still exists, but market is more kind of attached to JavaScript. So that's what we are betting on. That's what we told investors. So that's really what we focus on speeding up ETH, while being still ETH compatible. So when we decided this, then the next step was to decide how do we do this. And the solution that we have is pretty like straightforward. We have the side chain, so then there's like ETH main chain. Yeah, so there's like let's draw like this like ETH mainnet. And we have our side chain. And let's say we have some number of computers, servers on this side chain. And the thing is proof of stake chain, which is like ETH compatible. So we tested to make sure it works with Remix and Truffle and MetaMask and all of this stuff. And then obviously we also have to somehow connect the two. There has to be some connection here. And then like an important decision which we also like were thinking about, like the principal thing was miners. There are some networks which are mineable and some networks which are not mineable. Mineable means that pay people for putting servers in your network, participating in your network. So for instance, ETH is mineable, right? But for instance, EOS is not so much mineable because you cannot freely join EOS. No one.
You can delegate your
You can delegate. Right. So
very small portion.
Right. So, but it's not like so democratic as ETH. So kind of at a high level, what we realized is that like the perfect mining is where your money goes, the money that you print, because in mining, in many cases, you print money. You introduce inflation and you print it out of the thin air. So this money has to go to people who actually grow your network. So you have to produce this natural fit where you print money, but you don't just give it like to people who don't care about your network. You really want to stimulate people who care, so promote your network. And if you find this correct symbiosis, the network starts to grow. And so if you look, for instance, at ETH mainnet, right? It's not so optimized in this way. So miners, for instance, get paid, right? So you get paid for money. But then in the ETH mainnet, there are also 10,000 nodes, which are like more like altruistic guys, right? They do lots of work. They get blocks, they store them, they run EVM, they respond to requests, but all of those nodes are not actually getting paid. And there is lots of like tension now on the Ethereum mainnet, where these people are saying, okay, we're running this full nodes, but we're not getting paid, so we cannot increase our computational resources, cannot increase our storage. So in our network, we're trying to find a more natural payment scheme where everyone that does something in our network is somehow getting paid. And if we can find this way, then the network is going to grow. So this is kind of a very principal thing to us, for us, the economics. But the economics becomes really hard because these guys do lots of stuff. So they store files, they respond to requests. As you probably guys know, in ETH there is this call requests where the state of the blockchain doesn't change, but they just get some information, respond to requests, they do storage, they do computation. So you need to be able somehow to pay good people and not to pay bad people. And this problem is not only our problem, it's for every utility network.
Yeah, it's a free rider problem.
Totally, yeah. So for example, we met these people from a network called LivePeer. These people who do like video streaming, and they pretty much have the same problem, right? Like I want to pay people that encode video for me, and I don't want to pay people who are actually Byzantine or do bad stuff, right? So the way we solve this problem in our network, because it's a complex thing, we introduced this notion of, we call it decentralized quality of service or decentralized SLA, service level agreement, where, let's say we have some number of servers in our network, and by default, each of them gets the same bounty at the end of each month, so we pay them monthly, but we need to somehow measure performance of each of them, and if the server is misbehaving, we don't pay, right? So in the first iteration of our network, we're going to take a very simple formula. And the formula is that we have a larger network. And so if you are a server, every month you have 21 guys, other servers from the same network, randomly assigned to you. So it's like everyone is watching everyone. So at the end of the month, these 21 guys report on me and say, okay, Stan's server was okay, the latency was okay, it was responding to requests. It's kind of the metrics. And if every metric measured by these 21 guys is above the minimum we require, we pay this particular server bounty. And then if one of the metrics goes down, the average metric, right? Then we don't pay the bounty. So, but then now there are like 21 measurements. So let's say this guy is getting measured by its peers, and at the end of the month, let's say you measure latency.
So how does it prove the information that's been measured?
So let me give you an example.
Yeah.
So let's take a very simple mathematical example. So let's say this guy is like 21 other guys paying this guy measure latency, right?
Yeah.
At the end of the month, each of the 21 guys is actually reporting average latency that this guy measured. So you actually have like this line, and on the line you have
Just take a median pretty much.
21 points. So let me give you the algorithm that we are going to have in the first iteration of our network. not saying that that's the perfect algorithm, but it's the simple formula that we're going to start in the first iteration. So the formula is, now, very important thing is, in this proof of stake systems, there are some mathematical assumptions. So we always assume that less than 1/3 m of the guys are bad. And then that's something which is assumed in many proof of stake networks. All of our servers have the same stake, and we assume that on the chain, less than 1/3 of them are bad. So then we have this 21 measurements. Now, what we do in this case, on the left, we drop 1/6, and on the right, we drop 1/6, because these are the most outliers. These are the most measurements which kind of off the average.
Sure.
And then we take the median, for instance.
You're removing high percentiles and taking median.
And then somewhere here there's this line, this like standard. So at the end, so this is the median we found. And then if this metric is more than the standard, the metric is satisfied. Could be latency, could be response to API calls. You can create all kinds of metrics. What we plan to have, we're going to start with a simple metrics measuring script. But then we don't know what's going to happen. There could be all kinds of bad things that bad people may try to use to fool our network into paying them salary perform work. So this script is actually going to be dynamic. And so when there will be governance in our chain, and then if 3 months from start we see a particular bad behavior, we can always add an additional metric to the script, and then this is kind of a way to fight bad behavior.
So I have a few questions here. First of all, how does this 21 actually get selected?
Okay, so let me go into this part. So in many cases in our network, we need randomness. And there are actually, it's kind of a hot topic in the community, right? Yes. And we actually kind of tried all kinds of stuff and thought about all kinds of stuff. And how do we create this random thing? At some point, we were really excited by an algorithm which is called VDF, Verifiable Delay Function. There is an algorithm called VDF. And the idea is that, a number of nodes, let's say even one node, submits with this function VDF, which takes a long time to calculate, but once it's calculated, it takes short time to verify. So let's say the function VDF takes 10 minutes, right? And what you do, one guy, for instance, provides you a random number, R, and then the seed for the random, and then the seed for the random number generator becomes like VDF of R. And the idea is that this guy needs to provide things really fast, and so he's not able to calculate VDF, and that's why he doesn't know, what the result is. So although I'm providing a random number, I'm not able to know what the result is going to be. So I'm not able to fool the system or influence the system. So there are different types of ways to use VDF, but the fundamental problem that we encountered with VDF is that VDF needs this function, which, let's say, takes 10 minutes to calculate, right? The problem is that if you build a function like that in software, on Intel processor,
you can an ASIC and
exactly.
Speed up something.
Exactly. So that's what we faced. So it may run 10 minutes on Intel, right? But if you do ASIC, it may run like 10 seconds. Who knows, right? So because of that, this entire business with VDFs require you to have this ASIC, and this ASIC don't exist now. No ASICs like that. Ethereum Foundation recently announced that they're going to be building these ASICs and maybe even open sourcing this code for ASICs. So it may be that a couple of years from now is going to be something that you'll be able to buy easily and incorporate in your network. But since now this stuff is not available, and since we need to release pretty much our network in the summer of this year, we're not able to use VDFs. So after many sad moments because we really liked this entire mathematics. We decided it's unusable for us in 2018, 19, so we pretty much like killed this stuff. So instead of VDF, we're using pretty much the only other algorithm, which is working. And let me tell you guys about this algorithm. So yes, this mathematical notion, which is called common coin. And it was introduced like by mathematicians many years ago and was like not used much for anything, but now suddenly this blockchain, this whole like mathematics is used. And the idea of common coin is that you have like n people. Somehow you need to derive the random number, and you know that, let's say, as an example, you know that less than 1/3 of these guys are bad. So what you want to have is an algorithm for collective random number derivation, where each of these n guys somehow creates a piece of something, like a mathematical obscure thing, and send it to all other guys. And ultimately, when I get all of the pieces, I kind of glue the pieces and create a random number. Very important thing is that this requires at least 1/3 over n guys to participate, so bad people cannot just influence the number, because there has to be at least one good person in the system, and the random number is unpredictable. So if you, let's say, you require 1/3 over n guys, then the bad guys cannot influence, because it's kind of aggregation of entropy. You know, the resulting entropy is kind of the sum of everything. So even if in a group there's one good guy, when the entropy is aggregated, you're not able, the bad guys are not able to predict or pre-influence this stuff. So then there's only one algorithm, pretty much, which is good enough to solve this problem. And this algorithm is called BLS signatures. So this algorithm was derived in about 2001 by 3 people. So there is a professor, Dan Bonnet, at Stanford, and there's another, I think that's his PhD student, Ben Lin, and Shahan, another guy. They actually were thinking about this really interesting mathematical algorithm, where normally like, all of us using like signatures, and blockchain will use signature, right? Typically, a signature means that I have a private key, and then someone gives me information, Ilya gives me information, and so this information is in the private key, and Ilya has my public key and can verify this stuff. So this is like used everywhere, like in e-commerce, you go like to Gmail, like all of this public-private cryptography is used. And then now a threshold signature, something which they call threshold signature, is a bit of a kind of improvement on this technique, where I have like n guys, you know, I have like 10 people, let's say, and to create a signature, it's a collective thing. So let's say 6 out of these people need to sign a piece, and then when the signed pieces like glued together, you have the signature as a result. So the interesting thing, this interesting mathematical property, so you have the signature S, right, of a message. And the way I derive a signature, I have my key, so I sign my piece, and then out of the remaining 9 people, I don't care if 5 people send me their pieces, I kind of glue my piece and the 5 pieces I got from them, and I get this S. But a very non-trivial mathematical property of this S is that no matter which of those people, which subset of 6 I get out of 10, the result is going to be the same, which helps to prevent against bad people, because one thing which bad people can do is to withhold stuff. They don't have to send me an incorrect signature. If like, there are like 4 bad people, they will just not send me anything at all, and then my protocol loses something which is called liveliness. Liveliness means that the action has to complete, right? But in this example, if 6 people are good, and the signature requires 6 out of 10, no matter what the bad guys do, including like not sending their signatures to some people, sending to another, whatever happens, it's guaranteed that the good people be able to grow, and every good person is going to have the same result as. And since S in general looks like a pretty random number, this S provides very much like this common coin. So it's a random number which is derived by everyone, known to everyone, and can be used then for all purposes.
What are you using to sign?
So that's an interesting question. So depending on the application, you could sign different. You just need a random number, right? You just, let's say you have a block. Typically, you need to have like a random number per block. So you just, your blocks are like 0, 1, 2, 3, 4, 5.
You just sign the block.
And then you can introduce all kinds of modifications, improvements. And so anywhere in our network, when we need a random number, we can take either all nodes in our network or subset of nodes, and we always use this VLS signature. So
the threshold signature requires a setup, right?
That's another interesting question. Thank you. Yeah. So okay, let's talk about setup, which is totally another like set of.
That's pretty much the biggest problem with threshold signatures is the setup is quite complex. And
totally.
In the original paper, it was very interactive.
Mm-hmm. Totally. So for the setup, we studied these things a lot. There are several papers which provide this initial setup. The mathematical name of it, many people use this name DKG, distributed key generation. And distributed means that there's no trusted party, because for the threshold signature, you have all the keys, but you need to somehow generate those keys in such a way that everyone gets a key, but no one knows anyone else's key. So it's fully decentralized. And there's like an entire set of papers on how this key is derived. And there's an algorithm which is called joint Feldman. Which provides a number of steps to derive this key. But this joint Feldman algorithm is well known in the literature. You need to like exchange lots of messages. All of these guys send messages to each other. So this is well known. But some of these guys, as we just discussed, may just withhold their stuff, not send anything. So for this joint Feldman thing, they have to be somehow punished. And the punishment algorithm we do through blockchain. And let me explain how it goes. So let's say someone comes to us in our network. We have this large network, and someone comes, and these are our miners. They have the servers, they're getting paid. Someone comes to us and says, "I want like a 50 server blockchain." So pays using our token, and then we like randomly select like 50 guys here, and we're supposed to run a blockchain with these 50 guys. But each of those 50 guys needs to get this key, this like super important key for us, this K, which uses DKG. And the way it's done in our case is that on the mainnet, on the Ethereum mainnet here, there is something which we call a DKG smart contract. So all of these protocols in joint Feldman, all of these messages that like send to you, these guys don't send to each other directly, but they send them through this contract, through the DKG contract. Why? Because we punish them for just doing nothing, right? So we give them like 10 minutes. So and tell them, okay, guys, you have 10 minutes to exchange messages using DKG, and if each of them sends the correct message, there's a verification procedure. So each of them follows the protocol, everything is fine, the keys are derived, then they're super happy. If on the expiration of these 10 minutes, one of them either sends an incorrect message, which doesn't pass verification, or doesn't send anything at all at a particular step, we just stop the protocol and punish the particular node. Essentially charge money. We don't really know how much, but let's say like $100.
And then you restart again.
And restart again. Right.
So pretty much, if I just front run these guys on Ethereum constantly, I can pretty much just slash all of them and pretty much postpone this for a while.
how are you going to front run?
Well, there's a many transactions with some gas, right?
Uh-huh.
So I'll just send transactions with high gas, which will kick them out of the sample for 10 minutes. I mean, this is doable.
But this will require you to spend money.
Yeah.
Right.
I mean, this is an attack, right? Like I'm trying to pretty much somebody requested this chain, like a custom chain, for something, right? They are waiting for it.
So
it's an attack, it's denial of service attack, right?
So you are going to feel like increase the gas price for the entire block.
Yeah, like depending how they use, how they define the gas price for these transactions, I'm assuming they don't want to pay that much, right? Because this is a lot. I'm assuming this is a lot of messages for DKG.
No, and the typical time scale, money scale for this is that each of those guys will stake. So the typical staking, we don't know exactly how much it's going to be, but we can assume it'll be like $5,000. So this they stake $5,000. The typical amount they're going to get at each month, like from mining, maybe like several $100s. I don't know exactly, maybe like $500 each of them.
Am I going to get more? Is there less people?
Yes, I mean, we're going to talk about this. I'll tell you about economics, but let's say you get $500.
Yeah.
So to front run them, and if we see this problem, I think definitely we can either increase the time or they can pay more. It's a problem, but for the first version of the network, not such a,
So how many messages do you need for DKG?
So for DKG, typically each of them sends a message to each other. So
you have 50, it's each needs to send 50 transactions?
Yeah, it's actually going to be one transaction. It's just, they would actually put in the transaction many messages going to different channels. It might be a bit of a problem, but for the first, we'll see how it goes, this part. So that's the DKG. Now, coming back to your question about the bounty, currently in our network, the bounty is 2.75%. It's just, don't ask why it's at 2.75, like after all mathematical calculations. But, so we pay 2.75% per year, like
annualized of the total supply.
Yes. So if in our network, say like 10,000 servers, let's say we have 2.75%. Let's say our market capitalization is $100 million, right? 2.75% means $2.75 million. So if we have 1,000 servers, all of them functioning well, pretty much like paying 2.7K per year. So this naturally adjusts the number of servers in our network, because when the number of servers goes up, each of them gets less, and at some point it becomes not economic to actually join the network. So that's currently the economy. So if you look at Bitcoin or Ethereum, you always see that in a network there's like an initial stage where the network is underloaded, and most of the miners are getting paid by this inflation. When the network gets loaded, at some point there are transaction fees which are becoming not zero, and the hope is that when the equilibrium is arrived many years after, at some point the inflation goes to zero, it's halved every 6 years, and at some point the network becomes self-sustainable, paid by this transaction fees. So that's pretty much what we do, like many other people follow this. So that's the economics.
Right. So on this question, so pretty much, let's say we're 21 folks that are monitoring your specific node, right? So for us, it's actually beneficial to all collude and kick you out of the system because we'll get more money, right? Like for that specific month.
It's true, but for the most part, they won't care, because, say, to kick you out, the potential gain they have is very small, right? You have like 1,000 node network, and you select 21 of them. yeah, if you kick one node now out, you kind of increase marginally the bounty. But there's a very little gain. And what we see at this point is that all these miners are going to be like these generalized mining guys, and most of them are going to have pretty significant operation. They're going to have lots of servers, so it's a community. And I think, but that's a very important question. I think at some point.
But let's assume we have less than 1/3 of malicious, right? So we have 333 servers that, let's say, are run by a single entity for simplification. Then they have, statistically, they'll monitor a lot of other folks, right? So this will be more than 100 other nodes. So they can kick out 100 nodes per month. And then this goes to 900. And they now control more than 1/3. And then they can start actually affecting randomness. So even after 1 month of us just kicking out few servers, we can actually start affecting the random to BLS and DKG, right?
Yeah, potentially yes. But all of these systems, if you look at them, there are different security options, right? There is external attackers. Someone can do denial of service in your system. There is vulnerability, someone find a hole in your software. There's this insider thing that you see. But when these networks become realistic, some of the attacks you cannot potentially fix all of the small things from the beginning because the systems are complex, and if you just try to fix everything, you will just not be able. The system becomes too complex. So I think us and LivePeer, and maybe you guys, everyone who is creating this new generation networks with lots of servers, you kind of solve the problem when it's getting created.
It's trade-offs. It's all trade-offs. So it's just we need to be clear what are the trade-offs. Right?
Totally. So you start with something and you iterate. So I think an answer to all of those questions is like a lean startup technology where you start something with something simple. You see what the important problems are, you kind of fix them, and so that means that you have to have very important community and governance in your system. You should be able to react to threats. And in our system, at this point, we decided for the security response team so we're going to have a security response team, which is going to be decentralized, just security experts selected or elected by community, and the security team will have ability to, at some point, stop an S-chain, because you could have anything, you're guaranteed against, for instance, security vulnerabilities. You can wake up and your S-chain can be down. So there will be an election process, which we are still thinking about, but a simple model is that, let's say you wake up and your S-chain is compromised. So the S-chain owner votes yes, been compromised, and then the security response team looks at this and also says yes, they've been compromised, and then they decide how to roll back the chain, and they decide to come on points in time to which this chain is rolled back, and this is kind of diverse scenario. But my feeling is that you have to, with this kind of faster chains, you have to have scenarios like this, because there's no way to do an AI to prevent against all of the security problems.
Sure.
So you need to be kind of modest in the sense that you accept the fact that you can be compromised, and you have to find some reasonable way to solve this problem. So I think that's pretty much the solution we arrived at the moment for this part. So I think I can also tell you a little bit about our consensus.
Sure, yeah. I just wanted maybe to finish this actually. How do people become validators, and how does this two-way communication happen?
Okay, so how they become validators, everything in our network is based on this DKG and BLS that you discussed. So when there's a need to create a new S-chain, all of the nodes in the existing chain, they sign the BLS signature, and this BLS signature becomes the random number seed, which is used to randomly pick a certain number of nodes from our network, and that becomes our network.
How does new validator become like how I have a server, right? I have $5,000. How do I become part of this?
Oh yeah. So this happens like that. So you buy a server, and then you have to have also the deposit. So you buy our tokens, and you stake our tokens.
And
so
tokens are on ETH,
on the mainnet.
ERC20.
Yeah, exactly. And then actually one of the kind of decisions which you made was that to simplify our network, all of our management stuff happens actually on the Ethereum mainnet. So all of this bounty payments, node addition, removal, all is implemented through smart contracts on the mainnet. So your node registers using our ERC20 token on the mainnet, you deposit this token, and then you become part of the system. But originally you don't have any exchange running on you, but you still paid bounty. You paid bounty no matter whether you're loaded or not. But then at some point, some idea developer comes and says, "I want to have an S chain," and you get randomly picked. And then now you start serving an S chain. And an interesting thing in our case is that we provide also cheap S chains for developers. Let's say you don't want lots of performance, right? We run our stuff in Docker containers, and a single server can run up to 128 tiny Docker containers. We call it tiny chains. So essentially on each server, you only run 1/28 of all resources, such as CPU and storage. And then these Docker containers are joined into a blockchain, which is not so much of a performant blockchain, but it's going to be very cheap because on each server, you essentially use only like 128 of resources of each server. So we will have a flexibility in this case.
So how does this guys know about what's happening on the main chain?
So that's an interesting question. So that's really a question which we're like thinking a lot, right? So what we have now on Ethereum, definitely we have the mainnet, which functions well, but is expensive. What we want to have is have lots of our side chains, right? And it becomes like an AWS in a sense, or like internet, in the sense that every chain becomes like a server in the old language and serves a particular application. So regular internet, like you have like a hotel, e-commerce site, you have a hotel server, and then you have airline, you have airline server. So you have these logical things, and you have this loose coupling between different servers in the sense that typically on internet servers talk to each other through APIs. So the hotel server calls JSON API on the airline server, and the airline server replies back. So this kind of a loose coupling architecture, and we decided in our system to implement this loose coupling architecture. So all of our stuff is implemented using messages. Smart contracts on each network, Solidity smart contracts can talk to each other, send a message. So in particular, when this S chain wants to send a message to the mainnet, not all, but two or three servers on the S chain sign a particular message, and the message, we have an agent which relays this message to the mainnet.
How does the agent work?
And the way the agent works is that actually on each of those servers, there's a copy of the agent, and there is a time, maybe like 5 seconds, let's say 10 seconds with him, right? So in round-robin fashion, at least on the first version of our network, each of them gets to be the relayer. So if this guy is bad, and when the message is sent from this place to that place, it is originally sent by, it's like smart contracts, like a proxy smart contract on this net. So actually the message is first in the smart contract here, and then it's signed, but now someone has to relate it to this this proxy smart contract. So this guy is supposed to relate, but then let's say this guy is bad. Like 10 seconds after, this guy sees, well, okay, this guy was supposed to relay things, he didn't relay things, so this guy relays. So it's like a round-robin fashion in which all of those guys at some point get to be relayers. So on average, even if some of them are bad and don't relay, you'll get a message relayed. It's definitely not so fast as things inside, but for the most part, the messaging is used in our case for transferring tokens. So you pretty much freeze a token on the main net. This smart contract sends a message to a smart contract on this S chain,
How
and
does
a
that
clone
happen?
is created. So this message on the mainnet, these guys can just verify in a regular Ethereum way, verify the state root of
Right.
Ethereum. And so it's actually first in the smart contract here.
Mhm.
And then this guy verifies the state root and passes this message to the smart contract on this net.
You mean
Right.
that this? You mean the external person who wants to send the token? He actually like after block included, he sends it here.
No,
That's what you mean?
let me give you an example. So there's like on this net, we have this proxy smart contract proxy,
Sure.
and there's a proxy smart contract on this net, and there is a smart contract sender right here.
Yeah. But, I mean, he's outside of the network, right?
In this case, it's just a smart contract let's say this smart contract on this network on the
Okay.
mainnet. And there's like another smart contract on this net. So this guy sends a message first to this proxy here.
Well,
So it's
smart-
right here.
Smart contract don't send a message. It's a person who authorized the transaction that is.
Yeah. So ultimately, there's like user
Yeah.
usually, and the user. It could be also a user. It could be a smart contract. Could be a user. But one of them sends a message.
Mhm.
Actually, it could be different architectures. But in our architecture, there's also like a deposit box. So bank smart contract.
Mhm.
So user sends a message to that one. It doesn't matter. It's not so important. But ultimately, the message is here.
Yeah.
And it needs to be relayed to this.
Mhm.
So again, we have this kind of round-robin situation where there's a relayer, and one of these guys actually relays, but it actually all of them, or 2/3 of them confirm. You again have this 2/3 confirmation. So to pass the message, it talks to other 2/3 guys, creates a threshold signature, and then the threshold signature is verified.
Wait,
So-
so every node actually needs to run a full Ethereum client?
Yes, absolutely.
I see.
Every node runs fully zero client, and moreover, going back and forth here actually requires you to spend some
Yeah, some gas.
ether, and the way it's done, the owner of this gap is supposed to maintain this account, which shouldn't be zero, where this ether should be placed, and then it's up to the owner of the app how to reimburse, maybe ask users to pay, or someone has to pay this gas costs.
Mhm.
And this type of kind of DLS signature relay is also used by Dfinity, and also I think Polkadot also uses this kind of threshold signature based messaging. The idea is that the security of that depends on everything is getting signed by 2/3 of the guys, and so the security model, as you see again, that if 1/3 of the guys become malicious, the problem. So all of these proof of stake systems have this natural.
I mean, the question is how easy it is to get 1/3, right?
Definitely, and that's really a question I think that people will learn, and when the first generation of the networks will be released, people will see how important this problem is. It may be, and there are different discussions. It may be nodes will need to maintain some kind of reputation, because what you want to do for those side chains, and not only for that, even for live peer, for any utility network, you want to be able to keep the number of bad guys small, because if you have many bad guys, no mathematical algorithm can help. So maybe this can be done through reputation, maybe through governance. So at some point there will be some kind of way to enforce this, and it's a very important question in this industry. That's something that I think everyone is gonna, gonna address. Okay, so that's this part. And let me, how much time do I still have?
Yeah, what time is it?
Just, am I running late or?
We're not talking about near.
Yeah. Okay.
Just one minute.
Okay. What?
This black thing.
Oh.
Black is pretty bad.
Okay. Anyway, so that's it. Well, let me just go into a bit of a different world and tell you guys a little bit about consensus.
Sure.
So it's kind of a very interesting subject because we have lots of mathematicians in our company, and we're really interested not only in kind of in a theoretical, not only in practical application of that, but also in theory. How does it kind of connect to mathematics? And usually in mathematics, if you kind of understand things, they tend to be simplified. So we were like looking for like a simplified framework to understand how what this consensus, the thing is, how is it getting used, and to find some kind of a logical framework in our brain, how we can understand things. Because otherwise you see like these people are doing this consensus, that people are doing that consensus, like a zoo of different consensuses. Everyone says I'm has to have the best consensus, and like it's like becomes like really passionate, I think, people talking to each other. So we designed this framework, which is a simple framework. I mean, what's a typical like consensus? What are the typical steps of a consensus and what a consensus is? And so we're like talking about classic consensus. In a classic consensus, you're supposed to like you have multiple nodes, right? And really, what you have is on each of those nodes, there's this blockchain. So for instance, there's like blockchain here, and the blockchain is kind of composed, it's kind of glued together transactions. So you have this 1, 2, 3, 4 like transactions, and they which are like blocks. Actually, they added to the end of the blockchain in blocks. But really, what you want to have is that, and what attacker doesn't want you to have is that all of these chains kind of are identical, with the only exception of network delays. So I may have, for instance, like a longer chain here, like 3, 4, 5, and only 4 transactions here, but the parts which are the same on this node and on this node have to be the same. So it's not guaranteed that the chain grows at exactly the same time on every node, but the pieces which are kind of on the same nodes have to be the same. So you want them to be the same, the attacker wants them to be different, and that's like the entire like business of blockchain is about that. And so what you typically have, no matter what protocol you use, like Tendermint, for instance, like our friend like Zaki that you guys interviewed, Tendermint, or like Dfinity, or like Algorand, or all of these people. Actually, conceptually is the same, like small differences. So you have steps. And what steps do you have? Okay, the first step, number 1, it's a submission. Typically, you have users like submitting transactions like this. Okay, yeah. So submitting transactions to your network, so you have the submission. But users, like you typically have lots of them, and they're not like gonna be like cooperative, so they typically have your network and they're like throwing transactions on your network. And so when they throw them, you have some type of a pending queue on each node. Somehow these transactions, they don't actually go into blockchain right away. They go some kind of like stored somewhere and they hope to be included. So you have this pending queue. And then next step, someone has to create this out of this chaos. Someone has to create like a block candidate or maybe block candidates, because you may have multiple block proposers at the same time. You may have a single block proposal. So you have this block proposal stage. And whatever your algorithm is, you may have 1 block proposer at a time, like in EOS, maybe you have 5 block proposers, could be all kinds of variations, but someone has proposed blocks. Now this another important thing, which is called data availability. And this is really like an important concept, which means that let's say you have some type of an algorithm, you have the block proposer, and many of them, one of them, and at some point this block may win. Winning means that it may actually get committed to the end of the chain, and it kind of transforms from the block proposal to the block which everyone is supposed to have. If I'm a bad guy and I somehow manage to not to send a block proposer or to one of the good guys, this good guy is gonna get stuck. So what I would want to have as a bad guy is to somehow propose, everyone like accepts my proposal, maybe hash of the block. I don't have to set the entire block, maybe the hash of the block. So I said, they accept the proposal. And then everyone says, okay, we accept this block. I say, okay, I'm not gonna give this block to anyone, and everything is stuck. So because of that, if someone proposes, you have to somehow guarantee data availability, and there could be different methods, but this step has to be there. And so after that, there is a fifth step, which is, let's call it consensus in some generalized sense, right? And this consensus means that, okay, you may have at this point still multiple block proposals, but now you know that all of them are data available, or you can use the term safe. They are safe. And so what means that they are safe is that at least one good guy has the copy of it. Because if I am a good guy, have a copy of a particular block proposal, I can always give it to some other good guy. So the data availability or safety of a block proposal means that the mathematics has to guarantee that after this step, for every block proposal which is deemed safe and goes further to the further steps, at least one guy has this proposal. So then there is consensus, and it's kind of where you may still have multiple safe proposals. Somehow you have to select which of them wins, and then you somehow select which of them wins, and then it's kind of a finalization step. That's where like the proposal, the winning one, is committed to the end of the chain. If I'm a good guy, but I don't have a copy of it, I ask around all other good guys, and because I know it's safe, so I'm able to pull it. So this is this finalization step when the block proposal is added to the chain.
Well,
so
finalization also means that there will be no other block that will be replaced.
Exactly, not other blocks, right? So you have to also. There will be no other block. You have to guarantee also that one single proposer only had only one proposal, because otherwise I could send one proposal to one guy, another to another guy, and that would be a mismatch. So this is kind of framework. You can use this framework. You can look at Tendermint, for instance, and actually the state machine which is inside Tendermint, you can somehow map to this kind of logical framework. You can take algorithm and map it, and then it kind of becomes easy for you, because you can take a look at the particular protocol and you say, okay, what are the 6 steps, and how, like, conceptually at high level this is achieved. Now, let's go back to our protocol. So the important thing is data availability. So in our protocol, if I'm a proposer, I want to propose a block. The way it works is that if I'm a proposer, I have to send my block to everyone, right? But some of the bad guys may decide not to accept it. So I cannot guarantee that everyone will take my block. So what I do, I'm in parallel trying to send my block proposal to all nodes in the network. But once I uploaded the proposal to 2/3 of the nodes, I cannot wait anymore, because the other guys may not accept it. So I wait. So each time I upload a block proposal, I get a piece of a threshold signature. So as a result of this data availability step, I have a threshold signature which attests that I did upload my block proposal to 2/3
So
guys.
is there one block proposer in your case?
Multiple. Could be one, could be multiple, it's configurable. So this protocol works for multiple proposers, one proposer, everyone could be a proposer. Depending on how many proposers, it takes more computation and more network. There is a version where everyone is a proposer, and there's some great fairness about this version where everyone proposes. The bad guys cannot really change things, but really the critical thing is having this data availability receipt. Now I have proof that I'm a good guy. I uploaded my proposal to 2/3 of the nodes, and then I'm actually broadcasting this proof to everyone in the network. So even I'm sitting, I'm not a proposer. I'm just sitting in the network and I'm seeing what's going on. Someone sends me a proposal, but also sends me a proof that not only I got this proposal, but but also 2/3 of other people got this proposal. So there is a mechanic like that, and this proof verifies to me that this proposal is safe. So then I vote 1 if for a particular proposal, if it's safe, if I can prove that it's safe, and I can prove it's safe because I have this threshold signature. So there's like this algorithm which kind of I explained at high level, but the idea is that I vote 1 for a particular proposal only if I prove to myself that it's safe. It's owned either by me or by at least one honest guy, right? So I vote 1 in this case, and I vote 0 if I don't have a proof like that. So then at this point you have for a particular proposal, you have every node votes is a 0 or 1, and then an algorithm happens which is called binary consensus. The binary consensus are like zillions of algorithms.
Right, but you don't have binary. If you have multiple block proposers, you actually have 0, 1 on all of the
exactly.
proposals.
So for each block proposal, you run for each block. If you have 5 proposers, you actually have a vector of 5. So you hold 0, 1 for each of them, and that's how like Honey Badger works. That's how we work. So you end up running in this example like 5 binary consensus algorithms, and they have this funny name, asynchronous binary consensus algorithm. And also synchronous binary consensus algorithm. There's like the entire zone of them, but the point is that what you do, you run consensus on each of them, and 5 consensus is complete, and you have 0, 1, and if at least one consensus return 1, you can commit. But you could have situation where for several proposals, you return 1, so you could actually commit any of them. There has to be just some deterministic procedure to commit, like let's say 4 of them are 1s, and you use a BLS signature randomness to decide the priority if there are 4 1s, which block proposer wins. So there is also this type of a game going on, and this is something which we do, something that Honey Badger does. There's a blockchain at University of Sydney in Australia, also this kind of play with this vectors. So it's interesting thing. Now, the other thing I'm going to tell you guys in a very simple way what a binary consensus is. And this entire, I think, conversation is just an invitation to look at those things, because some of these algorithms are very involved. It's hard like to go into every detail, but I hope at least you get a feeling, how it works.
Just before we do that, what is the side of the block? Or like, how do you do this data?
That's great question. So in a consensus, there's no preset. There is like maximum size of a block, but the block proposal happens in Ethereum network. You have this 15 seconds time variation. So you wait 17 seconds, whatever you get in your pending queue, like you mine, make a block proposal. Don't have anything like that. In our case, is that I'm a node. I just committed a particular block, and I immediately do a proposal for the next block. So there are like lots of different policies or algorithms. The greedy algorithm is that I take whatever I have in my pending queue and all of this stuff, like trying to increase the throughput. The entire thing in my pending queue becomes the proposal, but this has to be somehow limited. So we can say, okay, it has to be like less than a megabyte or 10 megabytes. So the larger are the blocks, the faster is overall throughput of the chain, because
the networking cost will be huge, right? Because you want to send it to everybody pretty much to get signatures, and if you have multiple block proposals, they also send it to everybody.
So this is also another very interesting set of algorithms that you could use. So when you send a block proposal, you have this pending queues, right? So you kind of assume that like absent network delays, pending queues on each of the nodes kind of look the same. Most, like many transactions.
Filters and
so you can do lots of mathematics. You can for instance, like in the our first iteration, the way we do it, the proposal does not actually include transactions, it includes hashes of the transactions. It becomes smaller. So I push proposal, the guy on the other side sees, okay, I have all of those hashes, so it reconstructs proposals from hashes. If there are some missing hashes, it talks back to this guy, the source guy, and gets the missing transactions. These algorithms, we don't do this now, but could be actually even taken even deeper, because if you think how this goes, typically depending queues on each node will look very much the same. So if you ask two nodes,
set difference.
exactly. So you have all of this algorithm totally. So you have all of the algorithms related to kind of how, if you have two things which are actually almost the same, what amount of information you kind of pass between the two entities for the destination entity to reconstruct. So this entire like kind of potential for this part. Now let me go really fast into the ABBA segment, into binary consensus, just give you guys a feeling what the binary consensus is. So binary consensus, it was like a very interesting mathematical topic, and like some people call it Byzantine generals problem and stuff. And the classical mathematical problem is that there's like, maybe it's a wall, you know, it's a castle wall, and like two gates, like gate number 1 and gate number 2, and you have like n generals, like there's like this army, and in the army there's like a number of generals, and the army has to, like, next morning the army needs to decide: do we attack here on this wall, on this gate, or we attack here on this gate? And we assume that out of these generals, you know, most of them are really smart people, and there's a one like crazy guy or bad guy or Byzantine guy, right? So all of them, like all of the good guys, like, you know, they look at this particular situation, and maybe one of them thinks, okay, you can attack here, and another one makes a decision, you can attack here. But what's important that in the morning, all of the armies attack one of the gates, because if some of the soldiers go here and some of them go here, they may lose. But if all of them like concentrate there in one single place, then they will win. So you have this thing where initially each of the generals, let's say 0 is left gate and 1 is right gate, each of them independently decides, I would attack here, right? So each of them is like 0, 1, 1, 0, 1, 0, 0. And the crazy guy may also decide something, but since this crazy guy is totally crazy or random, you may assume that his decision is totally illogical, and he can, during the protocol, during message exchange, he can send any messages, wrong messages, correct messages. Actually, a random guy is the same as Byzantine, a malicious guy, because kind of like a monkey can like type a book.
Well, I mean, malicious can be more, like it can actually have, like, malicious can know the state of everybody else and actually affect it.
Exactly.
So it can be more, like, way smarter than just trying to.
Right, but if you want to protect against all of the actions of the random guy, you may assume that just by the very randomness, the random guy may just randomly generate a malicious strategy. So actually, all of the proofs actually assume the guy to be random. In the same way, like a monkey can like print like a Shakespeare, the random guy. So actually, just mathematically, you can prove that totally random guy. If you prove that any randomness results in consensus, malicious is the same. So this one of these guys are random. So what you want to have, that kind of start exchanging messages, calling each other, and you want to have several things. First of all, at the end of this protocol, you want all of them come to the consensus, to the same kind of decision. Is it 0 left gate or 1 right gate? And then next morning each of them will attack the same gate. So first of all, it has to be consensus 0 or 1. And its consensus has to be throughout all of the good guys. But then there's another very important property. If initially all of the good guys, all of them, decide 1, the result should be 1. Which means that none of them decided 0, and you don't know, maybe the 0 gate is not safe. Maybe the reason why they decided 1, because they clearly see that this other gate is like so strong, you can't actually break through it. So if all of 1, it has to output 1, and initially if all of the good guys say 0, it has to be 0. And this is kind of the entire this Byzantine consensus thing. Now, if we take now these ones and zeros, and just to give you guys a feeling, remember, in our case, 1 is 0. 1 means that the block proposal is safe, and 0 is unsafe. So if all of the good guys say that the proposal is unsafe, this means that that no one has a proof that its data available. So it should be 0 at the end. You cannot select this proposal for consensus. So if all of the good guys are initially 0, it has to be 0. And this fact is not so important. But what's important about the consensus, if all of the good guys say this proposal is unsafe, you shouldn't commit it, because otherwise. So now you see that this general problem has a direct kind of mapping to the proposal, whether it's being safe or unsafe. So these algorithms, there are lots of different versions of these algorithms in the literature. Some use cryptography, some don't use cryptography. We use a particular version, which comes from a group in France. There's a professor, his name is Mustafawi. I think that's how it's spelled, Mustafawi. You guys can Google for it. And you can Google Honey Badger paper, and the Honey Badger paper, because Honey Badger also uses this. There's also reference this. It's very nice consensus of Mustafawi, but that's something we use because it's pretty fast. In theory, we could take this Mustafawi consensus and use something else. But then what I forgot to tell you is that there's actually a very interesting mathematical proof that even like if one general is bad, there's no deterministic algorithm that solves consensus. So there has to be some randomness in consensus. So if everything is deterministic, the bad guy always has a strategy for the consensus to either never stop or output different values on different sides. So there's a very interesting theorem. It actually can be explained, but maybe not today. But there's actually a pretty simple explanation, and we are planning to publish a blog post, simplifying like how the theorem is arrived. But it's an interesting thing that the consensus requires some randomness. And the last thing about consensus is that consensus assumes some type of a network model. So these generals or the servers, they exchange messages. So the question is, what's the quality of this network? And there are
that's general control network.
Exactly. So, and there are all kinds of things. So all kinds
I actually have a question. I mean, I think, there's all kinds of things that there's a lot about consensus to study.
Yeah.
Sure. One question I have is, given you actually have, like as a block proposer, right?
Mm-hmm.
If you're collecting parts of the signatures from the people you distributed the thing, at the end you actually have a aggregated signature, which is a proof that 2/3 have seen it, right? So pretty much you're saying, like, why are you running binary consensus on top of it? Like if you have already proved 2/3, is it just because 1/3 of them can be malicious and they cheat you?
Yeah, so this is a very interesting question. And this entire consensus thing, it's a bit of mind-boggling. So for me personally, it took some time to kind of go into this kind of understanding this very interesting mathematics. So let's say you have a proof that this block proposal is safe. Then why do you need consensus? You could say, okay, you could commit it to your blockchain. Well, there could be another good guy, and the bad guys could have intentionally withheld the proofs from the good guy. So this other good guy does not have a proof. So when you commit a block, you shouldn't only know that this is safe, but you should know that all other good guys know that this is safe.
But in this case, so let's say there's two cases, right? There's a good guy who is a block proposer. In this case, he collected 2/3, which means at least 1/3 of those 2/3 is good guys.
Totally. So it's safe. Right.
So they will distribute it.
Right, totally.
And then there's a case where the bad guys is who proposing a block, right? So for him to show a aggregated 2/3 signature, he also needs to show it to 1/3, right, of good guys.
Totally.
So this guy will also distribute it.
Right.
So if you have one block proposer at least, and this block proposer collected 2/3 of signatures, it is like like we don't need to run another binary consensus. I mean, this is how. Like,
So, okay, but that is unfortunately another iteration. So you have one block proposer.
yeah.
The block proposer, let's say it's a bad but very smart bad guy, right? So the block proposer sent his proposal or her proposal to like 2/3. No, really, like 2/3 have the proposal. Then he has the receipt.
But he was helped.
And he sends the receipt to all of the honest guys,
Okay.
except one. So all of these honest guys are happy and say, okay, and they committed. But then there is this other.
They will broadcast it to others.
But then if they broadcast it, then you have another level of.
I mean, you have a gossip rate.
But the problem is if they broadcast it, you have to deal with like entire another swarm of worms because you're getting broadcast. You don't know if the broadcast you're getting coming from. You can mishandle the broadcast. So there are lots of things which you think it's easy, and the consensus kind of this potential infinity it stops because what consensus tells you it's not only that this is safe, but that every good guy knows that this is safe, and this is kind of a logical step, which is very counterintuitive. And like I had spent like my entire life in mathematics, so I was doing like AI, like machine learning, this and that. This is kind of one of the most strange parts, all of these asynchronous things, and you kind of have to take time to kind of move your mind. And took me, you're going through like exactly the same things, which I was going like trying to understand this stuff. And I think I understood this, but it took me like 6 months, like reading through literature and kind of getting to. But this is very interesting, and I strongly suggest you guys. You can find there's a Honey Badger paper, like lots of references. There is then this paper of Mustafawi, which is cited in the Honey Badger paper, and then from that you can like go and there are all kinds of consensus algorithms, like this entire like academic community working, and it's really interesting. But what's great for us, we are like using this stuff. So even though we're not like super experts in consensus, if we take these mathematical papers and implement them as proven in the papers, and also if we understand at least, the concepts, we know that it's secure. So we can build our security proofs by kind of referring to this other guys. But this is a very, very interesting subject.
Sure.
So
I think we're out of time, so
okay.
Thank you.
Thank you very much.
Please leave your comments and feedback on the video.
Okay, guys. If you have any questions, you can also send it to Ilya, and be happy to answer.